the world of electronics and communication, modulation plays a key role since it is the process of varying a transmitted carrier in order to convey information. There are three things we can change about a sine wave: its frequency, its phase, and its amplitude. In frequency modulation, or FM, we convey information by changing the frequency of the carrier. The two most common applications of frequency modulation are commercial FM broadcasting, or FM radio, and local two-way communications. Frequency modulated signals require relatively wide bandwidths. FM is normally only used at VHS and higher frequencies, that is, at frequencies above 30 MHz. FM is almost exclusively used to transmit audio, either speech or music. And as we will see, one of the major advantages of FM is that it can provide both high quality and high immunity to interference, fading, etc. FM signals are created using an FM modulator, the inputs to which are an unmodulated RF carrier and a low-frequency modulating signal. The result is a modulated RF carrier whose frequency continuously increases and decreases based on the amplitude of the modulating signal. Frequency modulation offers quite a few advantages over other forms of analog signal modulation. Because FM transmits information as changes in frequency, it's relatively immune to changes in signal amplitude, such as those caused by fluctuations in the received signal level, noise, and interference. This makes FM a good choice for mobile or portable communications, where the RF and propagation environment may be rapidly changing. And since amplitude is not used to convey information, FM can also use the so-called nonlinear amplifiers, whose efficiency provides an advantage in terms of power consumption and thus longer battery life. Again, this is important for portable operation. However, FM does have a relatively poor spectral efficiency compared to other analog modulation schemes, like conventional AM or single sideband, in that it requires much wider bandwidths. The width of an FM signal is a function of its frequency deviation. Remember that in FM, the carrier frequency F sub C changes based on the modulating signal. In other words, the carrier moves up and down in frequency as the modulating signal changes. A very important concept in FM is deviation, which is the current distance in hertz of the carrier from the nominal center frequency of the signal. This deviation can either be positive or negative. For example, a deviation of 15 kHz means that the carrier is currently 15 kHz above the nominal center frequency. In many cases, when people talk about the deviation of an FM signal, what they really mean is the maximum deviation of the signal, that is, the maximum distance away from the center. This value is a function of the design and configuration of the transmitter, and it's chosen to meet the requirements of the application and the amount of available spectrum. Deviation ratio is the ratio of the maximum frequency deviation to the maximum modulating frequency. The deviation ratio will be different depending on the application. For example, music has a relatively high maximum modulating frequency, and this in return requires a relatively high frequency deviation if we want good audio quality. On the other hand, normal human speech has a lower maximum modulating frequency, so we can use a lower deviation and still have intelligible signals. Deviation ratio is often used to group FM signals into two general categories: wideband FM, which has a deviation ratio of greater than 1, and narrowband FM, which has a deviation ratio of less than 1. Let's look at the differences between these two different categories of FM. Wideband FM generally has a relatively high maximum deviation, usually 75 kHz, and a high deviation ratio, typically about 5. As mentioned earlier, using a larger value for deviation provides better audio quality, especially in the case of music. But this also increases the resulting bandwidth of the FM signal. As you might expect, wideband FM is most commonly used by commercial broadcasters. On the other hand, narrowband FM has a much lower maximum deviation compared to wideband FM, usually only 3 to 5 kHz. By definition, the deviation ratio of narrowband FM signals is always less than 1. And in practice, they tend to be somewhere around 0.5. Although this can vary widely between ranges and applications. This lower deviation ratio means lower audio quality, but also a narrower signal bandwidth. And thus, narrowband FM is normally used for two-way voice communications. Typical channel widths are usually 12.5 or 25 kHz, although these two can vary depending on the application. We can approximate the bandwidth of an FM signal using the Carson's rule. This rule is named after John Renshaw Carson, who first formulated it in 1922. Carson's rule defines the bandwidth of an FM signal as a region that contains 98% of the total signal power. And this can be computed by adding the maximum frequency deviation to the maximum modulating frequency and then multiplying the sum by 2. For example, a commercial FM broadcast station with a maximum frequency deviation of 75 kHz and a maximum modulating frequency of 15 kHz would have a bandwidth of approximately 180 kHz. FM broadcast stations are spaced 200 kHz apart to provide an additional guard band to prevent interference between adjacent frequencies. To simply put it all, frequency modulation is the process of varying the frequency of a carrier signal in direct proportion to the instantaneous amplitude of a message signal, and it requires significantly wider bandwidths than the other analog modulation types. An important concept in FM is deviation, which is the distance that the carrier moves from the nominal center frequency. And we can use the Carson's rule to approximate the bandwidths of an FM signal. While on the other hand, the frequency modulator is the electronic device that being used that control the carrier signal's frequency based on the variations of the message signal. The results in a modulated output where the carrier signal shifts in frequency according to the information being transmitted.
Let's dive into the components that make frequency modulation possible. A frequency modulator is made up of several key parts, each of which perform a specific role in the modulation process. The first one is the most commonly used for this purpose, which is the varactor. The varactor diodes are one type of p-n junction diode whose internal capacitance can be changed by applying the reverse bias voltage. So, these diodes are also known as the varicap diodes. And this term, varicap, refers to the variable capacitance. Similarly, the term varactor refers to the variable reactance. So, in this diode, as we change the applied reverse bias voltage, its capacitance, or in other words, its reactance, will change. And this property of the varactor diode is useful in many applications, particularly when we want to change the capacitance in the circuit using the external applied voltage. Then, these varactor diodes are very useful. So, because of these properties, they are used in the RF communication system. And this is the symbol of the varactor diode. So, this symbol indicates that it is a p-n junction diode. But unlike the normal rectifier diode, it is intended to be used as a capacitor. So, to understand the working of this varactor diode, first of all, let's see how we can change the capacitance of the parallel plate capacitor. So, for a parallel plate capacitor, the capacitance can be given as C is equal to epsilon of A divided by D, where A is the area of the plates, while epsilon is the permittivity of the dielectric material. And here, this D is the distance between the two plates, or the thickness of this dielectric material. So for a fixed value of epsilon and the area, if we change the distance between the two plates, or in other words, if we change the thickness of this dielectric medium, then the capacitance will also change, or the capacitance of the capacitor will also change. So, with the same concept, the capacitance of the varactor diode is varied. Now, as I said, this varactor diode is also one kind of p-n junction diode. In the p-n junction diode, this depletion region gets formed at the junction, where this p-type and the n-type material meets with each other. So, this p-type material contains the excessive amounts of holes, while this n-type materials contains the electrons. On the other hand, if you see this depletion region, then it is depleted of the charge carriers. So, in a way, this p-n junction diode behaves like a capacitor. That means here, this p-type and the n-type region acts like conducting plates, while this depletion region acts like a dielectric medium. And we know that this p-n junction, as we change the applied reverse bias voltage, then the width of the depletion region changes. As we increase the applied reverse bias voltage, then the width of the depletion region will also increase. And as the depletion region width, the width increases, then from this equation, we can say that the value of the capacitance will reduce. That means we can say that this capacitance is inversely proportional to the applied reverse bias voltage. And if we see the exact relation, then it can be given by the following expression, where V is the applied reverse bias voltage and Vf is the forward voltage, or the built-in voltage of this diode. And here, this CO represents the capacitance of the diode whenever it is unbiased. Now, in this equation, this value of the N depends on the doping profile of a varactor diode. So, based on the doping profile, there are two types of varactor diodes. The first one is the abrupt varactor diode, and this is the doping profile of the abrupt varactor diode. So, as you can see, in this p-type and n-type region, the doping concentration is uniform. But at the junction, there is an abrupt change in the doping profile. So, this type of junction, the value of N is equal to 1 by 2. So, usually, these normal p-n junction diodes have this abrupt junction. On the other hand, this is the profile of the hyper-abrupt varactor diode. So, as you can see, on both sides, the doping concentration reduces with a distance. And for this type of doping profile, the value of N is equal to. So from this expression, we can say that for this hyper-abrupt junction, as the value of this reverse bias voltage increases, then there will be more change in a capacitance. So in general, for the normal p-n junction diode, if we see the curve of the capacitance versus the applied reverse bias voltage, then it will look like this. That means, in general, any diode can be used variable capacitor. But the varactor diode are optimized and manufactured in such a way that they provide more change in the capacitance with a reverse bias voltage. So now, let's see the equivalent circuit of the varactor diode. So, if we apply the reverse bias voltage, then in that condition, the equivalent circuit of the varactor diode will look like this. This RR is the reverse resistance of the diode, and this RS is the ohmic resistance. Now, typically, the value of this reverse resistance is in mega ohms, because whenever we reverse the bias, then only a leakage of a current or the reverse saturation current will flow through the diode. And that current can be represented by this reverse resistance. So, for the varactor diode, to minimize the leakage of a current or the reverse saturation current, this reverse resistance should be as high as possible. So, this is the equivalent circuit of the varactor diode at the low frequencies. But whenever it is operated at the high frequencies, then we also need to consider the parasitic capacitance and the inductance. So, this is the equivalent circuit of the varactor diode at the high frequency. So, as I mentioned earlier, the varactor diodes can be used in the tuning circuits. For example, as shown in the figure, here the varactor diode is employed in the tuning circuit. So, for the given tuning circuit, the resonant frequency is equal to 1 divided by 2 pi times under the LC or under the root LC. C is the summation of this CT and CC. So here, this CT is the capacitance of the varactor diode, while the CC is the coupling capacitor. So as you can see, as we change the applied reverse bias voltage, then we can change the value of this capacitor. So in this way, we can tune the circuit to the particular frequency. So these varactor diodes are used in the FM receivers as well as in the communication equipment where the circuit needs to be tuned electronically. Apart from that, they are used in the RF filters as well in voltage control oscillators. So these are some parts of the applications of the varactor.
Now, to understand crystal oscillators and voltage-controlled oscillators, we'll start with a quick explanation of what an oscillator is. Broadly speaking, an oscillator is an electronic device that produces a repeating signal or waveform. This is usually, but not always, a sinusoidal signal. Oscillators are one of the most fundamental components in a wide variety of electronic devices, and many RF devices have multiple oscillators. The primary characteristic of an oscillator is the frequency of the signal that it generates. But we're also often very concerned with the quality or the purity of the oscillator. For example, how stable are the output frequency and power? Are significant harmonics or spurious signals also present? Since the quality of an oscillator's output can have a significant impact on the function or behavior of the overall system, it's important to measure or characterize oscillators. For some oscillators, the output frequency is a constant or fixed value. That is, the frequency depends on the design of the oscillator or on the components in the feedback network. In other cases, the output frequency of the oscillator may be variable. The frequency can be dynamically changed based on an external input. There is also an oscillator called LC oscillator. But since most of the LC oscillator are simply not stable enough to provide a carrier signal, that's why crystal oscillators are used to set carrier frequency, because it is a type of electronic oscillator that uses the mechanical resonance of a quartz crystal to generate a stable frequency. The crystal's unique physical properties allow it to oscillate at a precise frequency when an electric current is applied. This frequency is determined by the size, shape, and cut of the crystal, making crystal oscillators highly stable and accurate. Crystal oscillators are widely used in applications that require high-frequency precision and minimal drift over time, such as in clocks, watches, computers, radio transmitters, and GPS systems. The key advantage of crystal oscillators is their high-frequency stability, which makes them ideal for applications where maintaining a consistent and reliable frequency is critical. On the other hand, a voltage-controlled oscillator is an oscillator whose output frequency is controlled by an external voltage called the tune or control voltage. In this presentation, we'll refer to this voltage as V-tune. For example, increasing or decreasing V-tune causes the oscillator output frequency to increase or decrease. The tuned voltage may be changed in discrete steps as shown here or continuously. There are a wide variety of VCOs with different form factors and different specifications or operating parameters. VCOs are also used in a wide variety of applications. One of the most common applications of VCOs is in phase lock loops or synthesizers, which will be discussed later. For example, we can create analog FM modulation by continually varying V-tune, or we can implement FSK or frequency hopping by changing V-tune in discrete steps. Another place where VCOs are helpful is in radar applications, in particular in linear FM or chirp radar and in FMCW. Just as there are many different VCO applications, there are also many different ways of designing VCOs. Some common oscillator designs have names such as Colpitts, Hartley, and etc. A key component in most VCO designs is a varactor diode, which was explained by Kuya Jumari earlier, which acts as a variable capacitance. The choice of which design to use affects the VCO's performance and characteristics. And in most cases, various trade-offs must be made. For example, how wide should we make the VCO's frequency or tuning range? A wideband VCO can be used to cover a wide range of frequencies, and this eliminates the need for multiple narrowband VCOs. This is particularly useful in radar or electronic warfare applications. On the other hand, narrowband VCOs generally have better phase noise and would be more suitable for use in a PLL, which will be elaborated later. Measuring the behavior or characterizing the VCO is therefore an important part of the VCO design and debug process. Now, let's talk about how VCOs are characterized. There are various methods and instruments that can be used when characterizing VCOs. For any test setup, there are two very important requirements. The first is the ability to supply very stable and highly precise fixed and variable voltages. The second is the ability to very precisely measure changes in the VCO's output frequency, power, phase noise, etc., as one of these voltages is changed. Because VCOs are a special type of oscillator, phase noise testers with integrated voltage sources are often used to characterize VCOs. In most cases, these instruments also provide automatic measurement of common VCO characteristics such as output frequency versus tune voltage. And this automation both increases accuracy as well as decreases test time. Let's look at an example of a typical VCO test configuration. Three connections needed to be made to our VCO. First, the VCO needs a supply voltage to operate. This is normally a fixed voltage. Next, we connect the tuning or control voltage V-tune. This is a variable voltage that controls the VCO output frequency. And finally, the VCO RF output is connected to the RF input of our instrument, which then measures and plots the output characteristics of our VCO as a function of the variable input voltage.
Phase modulation is a form of modulation where the phase of a carrier signal is varied in proportion to the amplitude of the input signal. Unlike amplitude modulation, which changes amplitude of the carrier, or frequency modulation, which varies the frequency. Phase modulation alters the carrier signal's phase at specific points in time. This allows information to be encoded when the phase changes of the signal, making it a widely used technique in communication system. A phase modulates by adjusting the phase of the carrier signal based on the incoming message signal. The message signal controls the amount of phase shift applied to the carrier. This phase shift can be continuous or discrete, depending on the modulation scheme being used. Typically, the phase modulator is implemented using analog components such as voltage-controlled oscillators, varactors, or mixers. The modulated signal is then transmitted over a communication channel, and the modulator at the receiver extracts the original message signal from the phase modulated carrier. A phase modulator can be considered better than frequency modulation. In certain applications due to its higher bandwidth efficiency and simpler implementation in digital communication systems. And phase modulation is encoded by varying the phase of the carrier signal, which typically requires less bandwidth compared to FM, where the frequency of the carrier is varied. Additionally, phase modulation can be offer or improve performance in a certain noise environment, particularly when the noise is primarily amplitude based.
The FM demodulator is central to the function of any FM-based communication system. In the case of FM radio, the demodulator processes the received radio signal, converting it into an audio signal that can be amplified and heard through speakers and headphones. In more complex communication systems, such as those used in satellite communication, two-way radios, or telemetry, FM demodulation plays an essential role in ensuring that the transmitted data is faithfully recovered and interpreted by the receiving system. Several methods are used for FM demodulation, each with its own advantages and specific applications. Some of the common techniques include: first, the slope detector. It is one of the simplest types of FM demodulators and generally less efficient than other methods, and can produce more distortion, particularly when the frequency deviation of the FM signal is large. Second, pulse averaging discriminator. It operates by converting the frequency variations of the FM signals into pulse-like signals. It has a relatively simple design and can provide good performance in environments with minimal interference. Third is the quadrature detectors, which offer high accuracy and are often used in systems where high-quality signal recovery is required, such as in professional radio communications and digital broadcasting. Lastly is the phase lock loop, or the PLL demodulator. The PLL is one of the most widely used methods for FM demodulation due to its stability and accuracy. The PLL adjusts the frequency of the oscillator to match the frequency of the FM signal. PLL demodulators are particularly valued for their ability to lock onto the carrier frequency, providing high fidelity and good noise immunity. Overall, the FM demodulator is an indispensable component in systems that rely on FM transmission. The choice of demodulator depends on factors like signal fidelity, complexity, and system requirements. Whether in simple radio receivers or advanced communication systems, each of these demodulator types plays a crucial role in ensuring that the transmitted information can be faithfully recovered and used. FM circuits consisting of frequency modulators, phase modulators, and frequency demodulators are integral components of modern communication systems, playing a pivotal role in both signal transmission and reception. Each of these circuits is tailored to handle specific aspects of frequency modulation, ensuring the reliable encoding and decoding of information across various communication platforms. Together, these FM circuits enable the efficient transmission and reception of a wide variety of information ranging from audio and FM radio broadcasts to digital data and telecommunications and satellite systems. Each circuit, from modulator to the demodulator, plays a crucial role in maintaining signal integrity, reducing errors, and ensuring that the encoded message is accurately recovered. The versatility and robustness of FM modulation and demodulation makes these circuits indispensable in numerous applications, from entertainment and broadcasting to critical communication infrastructure, making FM-based systems highly reliable and effective for both analog and digital communications.